This is Lab 1 Charge Tapes by Dhilan Nanji. Introduction, background, purpose, and overview. Objects gain a charge due to receiving surpluses or deficits in electrons which have a negative charge through contact with other objects. Examples include rubbing a balloon against your hair and pulling apart pieces of tape as shown in the experiment. A surplus of electrons gives an object a negative charge while a deficit of electrons gives a positive charge. The purpose of the charge tape slabs is to approximate the required net charge on two pieces of charged tape, we assume both have the same charge, to float one piece of tape over the other. Since we are looking for repulsive forces, it is expected that the tapes have charges of a matching sign. Using a negatively charged pen, I found that the tapes are positively charged as they were attracted to the pen. In this lab, a piece of charged tape was suspended over cardboard shelf dividers and floated using a second piece of charged tape. Both were positively charged. The upper tape began to float at about 2.0 centimeters and had a net charge of 1.76 times 10 to the negative 8th coulombs. To determine this value in a mathematical model using Coulomb's law, the gravitational force on the upper tape and the measured distance at which the upper tape began to float were used. The first main concept for this lab is Coulomb's law, which they said the electric force is equal to 1 over 4 pi epsilon naught times Q1 times Q2, which are the charges of both particles, divided by the separation distance squared, which is equal to K, the condensation of the previous constants, times this charge of the upper tape squared, divided by the separation distance squared. Newton's second law states that the net force is equal to mass times acceleration, and in this case we have zero acceleration of the upper tape, so the electric force must equal to the gravitation force. Two models were used for this experiment, a point charge model and a line of charges model. The results were shown to the right and the code is in the description. The top image depicts the line of charges model and the bottom image depicts the point charge model. Prior to the actual experiment, the single charged tape was attracted to my hand, a neutral object. The tape was attracted to the negatively charged pen, and when paired with another charged tape, the tapes repelled each other. The length of the floating portion of the tape was 0.154 meters. The mass of the floating tape, using the 1 gram per meter approximation, is 0.000154 kilograms, or 0.154 grams. This was found by multiplying the length by the conversion factor as shown in this equation. The magnitude of the gravitational force on the floating piece of tape is 0.00151 newtons, as shown in this equation. The distance between the two tapes when the upper tape began to float was 2.0 centimeters or 0.20 meters. The magnitude of the electric force on the floating tape, as given by the lines of the charge model, is approximately 1.51 times 10 to the negative 3 newtons. The approximate electric charge on the floating tape was 1.76 times 10 to the negative 8th coulombs. This value was provided by the lines of charges model. The 8.19 times 10 to the negative 8th value is from the point charge model and from my calculations, which sets the gravitational force equal to the electric force, which allows the gravitational force to be substituted for the electric force in Coulomb's law. Since the gravitational force constant K and separation distance are known, Q can be solved for. The sources of error were assumptions made in my own human error. My hand started to shake, and this may have made the distance measurement less accurate. The assumption that both tapes have the same net charge is likely false, as they may have been handled unevenly and lost uneven amounts of charge, but it may be a helpful middle value. The assumptions made for the point charge model are that all of the excess charge on each tape is condensed into a single point and only those two points interact with each other electrically. The line of charges model does not make this assumption to the same extent as a line of charges are used, but it essentially condenses the charge distribution to lines of point charges. Both models assume the same net charge is present on both tapes. Here are my calculations regarding the deficit of electrons and the ratio of atoms that lost electrons. The deficit of electrons was found by dividing the total charge, as calculated from my data, divided by the charge of a single electron, or the magnitude of said charge. It gives 5.12 times 10 to the 11th electrons. The ratio of atoms that lost electrons to the total atoms on the surface of the tape is the area of the tape divided by pi r squared of the atom to get the total number of atoms. Then the ratio is the electron deficit divided by the total atoms, and that gives the ratio of the atoms that lost electrons to the total number of atoms on the surface. If protons and electrons switched charges, the net charge of each tape was flip signs, in this case from positive to negative, but they would still repel due to being the same sign. For the y question, the estimated value, also from the point charge model, is larger than the value found in the line of charges model. This is because the charge distribution is different, and this changes how the gravitational load is balanced by electric force. Since the line of charges model is somewhat closer to the real charge distribution, it is more likely to be closer to the true required net charge to float the upper tape. This experiment used the principles of Coulomb's law and the Newton's second law to approximate the required net charge to float one charged tape above another at a given distance. Two models were used in an attempt to determine this, a point charge model and a line of charges model. My calculations in the point charge model gave a value of 8.19 times 10 to the negative 8th coulombs for this net charge. It was also found that 1.76 times 10 to the negative 8th coulombs was this net charge based on the line of charges model, which is likely more accurate due to being more representative of reality. Both of these values are approximations, as it is assumed that both tapes have the same net charge, which is likely false, and the line of charges has several orders of magnitude fewer charges than are present in reality.